So this is section 2.2. And so I'm going to put it here and just so we can refer to it. Tangent. So the tangent graph. And over here I'll put cotan. Tan and cotan. And then down here I'm going to put, let me separate these, and I'll put secant and cosecant, so we can refer to all four. And so same thing, one more time on the asymptotes. So for tan and secant, they have their asymptotes at negative pi over 2 and positive pi over 2, and secant's the same thing because they're both the non-co-graphs. So both the non-co-graphs have their asymptotes at negative pi over 2 and positive pi over 2, and both the co-graphs have their asymptotes at 0 and pi. And then what do the graphs do in between? The tangent does a snake, and the cotangent between his asymptote lines does an upside down snake, because cotan's upside down of tan, huh? So that makes sense. What does the secant do? The secant and the cosecant, they both do U-shapes starting at 1 between their asymptote lines. And then, then there's another asymptote, and it does a U-shape down at negative 1. Same thing over here. There's another. These continue forever, as you know. Negative 1 over here, and he does a U-shape down. So there we go. There's the general, again, one more time, there's the general 4 graphs. So the graphs continue forever, even tangent, more snakes to the right and left forever, cotangent, more upside down snakes to the right and the left forever. So both the co-graphs are between 0 and pi for their asymptote lines. Both the non-co-graphs between, the tangent secant, between negative pi over 2 and positive pi over 2. And the secant and cosecant are U-shapes, up, down, and tan and cotan are snakes, up or down. All right, so with that basic game plan, that's about 90% of the battle. Let me show you how it works. So let's do some homework now. So question number 1. Here we go. So we're going to play multiple choice here, or match them up, I guess it's called. Match them up. So we have 4 tangent graphs, and we're wanting to match it up with the right one of those. Now notice, they're not just giving us regular tangent. They're messing with them, huh? Right? This one has a negative in the front. This one has a plus pi over 2, minus pi over 2. So all of those are going to do something to the basic tangent graph, which is the basic snake that goes between negative pi over 2 and positive pi over 2. So what's it going to do to have that weird stuff on the inside? Well, last week in 2.1 we talked about sine and cosine. I gave you a whole game plan for that, right? It's all the b. I gave you the phase shift is negative c over b, and the period is 2 pi over b, and all those things, and that worked great. And that's a good way to do sine and cosine because there's a lot of complexities with sine and cosine. But we're going to do a different game plan today for these 4 trig functions. We're not going to identify A, B, and C. They're there and everything, but an easier way to go is to identify where the 2 asymptote lines end up, because they will move based on, the whole graph will move, every part of the graph, the snake, the asymptote lines, everything will move depending on what they stick inside the parentheses. That'll move graphs around and do stuff to the graph. Well, how do you know exactly what it does? All you got to do is find out where those 2 new asymptote lines are, and you got it. This will be easier, really, I think, than what we did before. Let me show you. So let's take like this second one. I'll come back to the first. Let's just do this one. Tangent of x plus pi. What's that going to do? So y equals tangent of x plus pi. What is that going to do to the graph? I mean, I know how the normal tangent looks, right? The normal one, like we've said a couple times already today, has asymptotes between minus pi over 2 and pi over 2 with a snake in the middle. Okay, that's the normal one. What's going to happen when you stick that plus pi in there? Well, the easy way to figure that out is just you take whatever they put on the inside, this, and you just stick it between negative pi over 2 and positive pi over 2. And then you solve. Because whatever's on the inside, as it's between negative pi over 2 and positive pi over 2, that's where the asymptote lines end up. So if you solve that, you'll find it. So let me show you what I mean. Let's take x plus pi, which is the inside, and we set up this 3-part inequality. Have you seen these before? They call that a compound inequality. It's got 3 parts, left, middle, right. It's not really a big deal. If you want to draw lines, you don't have to, but if it helps your vision. Left, middle, right, and we just simply get x alone. If you just get x alone, you'll find out where the new asymptote lines are. So what do I do to get x alone up there? X is right here. Don't worry about like everything in the world. Just focus in on x. X is saying, I want to be alone. That's what x is always saying. So what do we do to get x alone? Subtract that pi. Does that sound good? That's exactly right. Subtract that pi, because boom. And whatever you do to one part, you just do the same thing to all 3 parts. Right? You got to treat all 3 the same. Because the left is smaller than the middle, which is smaller than the right. So if that's true and you treat them all the same, the left will still be smaller than the middle, right? If I just think about 3 numbers, if I go 2 is smaller than 10 is smaller than 15, and I subtract 1 from all of them, they will still be in that hierarchy, won't they? That's the logic we're using. If you got a small, medium, and large, and you subtract or add or whatever, or multiply the same thing to all of them, they're still going to be small, medium, and large, aren't they? So that's, you just do the same thing to all 3 parts, and their relationship is preserved. Okay, so where does that leave us then? Well, that means we gotta work this out. How do I do this right here? How do I do minus pi over 2 minus pi? How do I combine those? Do what's that? Make it 2 pi over 2. Good idea. Yeah, whenever a whole number is interacting with a fraction, you put it over 1, first off, right? So it looks like a fraction, you with me? So they both look like fractions. It's the same thing, right? Pi over 1 is just pi. And then, yeah, you got to make common denominator, don't you? You guys good here? This is probably the hardest part of it. Multiply top and bottom by 2. So then this becomes minus pi over 2 minus 2 pi over 2, which will be minus 3 pi over 2. Good so far? Everybody tracking with me there? So you see what I did there? So so whenever a fraction interacts with something that's not a fraction, put it over 1. So it looks like a fraction. Multiply top and bottom by 2, common under. And then this is minus 1 pi and minus 2 pi, which is minus 3 pi over 2. Other side, same thing. Got to put this over 1. Multiply top and bottom by 2. So we get pi over 2 minus 2 pi over 2, right? This guy and this guy. So that's 1 pi over 2 minus 2 pi over 2 is what? Minus 1 pi over 2, or just pi over 2. Minus pi over 2. Good? Common denominator. So that's it. That's where the new asymptote lines are. So they've moved. So let me get rid of the normal looking tangent here. And I'll say, okay, and that's it. You just find those. So the new one, instead of tangent x, I have tangent of x plus pi. And what ends up happening? What does that cause? What shift does that cause in the graph? The asymptote lines end up going between negative 3 pi over 2 and negative 1 pi over 2. So you just go, okay, here's one. I'm just going to call that negative 3 pi over 2. And then this one here, negative pi over 2. And then in the middle, I just put a snake. Done. And then I go find the one that looks like that. Multiple choice. Is that making sense? This is pretty much what we're going to do for the next hour and a half on all of these. Is whatever they give you on the inside for any of these functions, tangent, cotangent, secant, cosecant, we're just going to stick it between the 2 boundaries that we know of, which is negative pi over 2 to pi over 2, or for secant, for 2 of them it's 0 to pi, isn't it? And then just solve for x. get down to here, and that's where the two new asymptote lines go. That helps you locate the two boundary lines, the two asymptote lines, and then you just stick the graph in the middle, whatever that may be. In this case, it's a snake going up because it's tangent. Now, that repeats forever. You know, there'll be another one over here, you know, snaking along forever, like that. You know, it'll go and go and go. But it's been moved. So let's go back and look for the one that's been moved, negative 3 pi over 2 to negative pi over 2. Let's go back. Which one is going between negative 3 pi over 2 and positive pi over 2? It's hard to tell. They're not really showing me the left, are they? Yeah, I think it's the first one, as I agree. Let's show it carefully. First off, why is it not number 2? I'm thinking it's number 1. Let's eliminate the others. Why is it not number 2? Can you see number 2 is going between 0 and pi? That must be pi, even though that arrow's in the way, because pi over 2 is in the middle of it. So that must be pi. This boundary must be pi. This is, of course, 0. Yeah, so we know it doesn't. How about that? It doesn't hit 0. Right? Look back. Right? The snake goes through the middle of 0. Mm-hmm. It doesn't line out at 0. Mm-hmm. Right? Everybody see that? Right? Because the boundaries went from negative 3 pi over 2 to negative pi over 2. That's what we found out here and here. How did I know it went through the middle here? Well, from there to there is a pi, isn't it? Is that okay? Do you realize that's a pi? Because it's 2 pi over 2, which is pi. Everybody see that? So then this is another pi. All right, so getting back, it's not this one. No way, it doesn't. It has to go through the origin. That one's not hitting there, so it's not number 2. It's not number 3. Number 3, that's going down. Notice those are going down instead of up. That's the only one where they're... Oh, wait a minute, no, 4. 4 is also going down.
It's because there's 2 negatives.
Yeah, that's got to be this guy and this guy with the negatives in the front. Remember how negative in the front of a graph turns it upside down? We saw that with sine and cosine. Same thing with all these. For any graph, not just trig. You go to pre-calc. I'm teaching pre-calc right now. I'm talking to them about negatives in the front of a graph always turn it upside down for any graph. So yeah, so those 2, 3 and 4 are those 2 that have negatives in the front. So anyway, so this is number 1, isn't it? Good there. So what must number 2 be then? The other positive one, that one, huh? Because it's the only other one that has a positive in front, which makes the snakes go up instead of down. We okay with that? Now, I could go through the same work. In fact, why don't I real quick, just to prove it. It's x plus pi over 2. So let's just do that real quick. Y equals tangent x plus pi over 2. Can you do the same thing for that one real quick? Can you find the two boundaries? We'll go much quicker on the others, but I just want to go slow on this one. Can you take that one and find the two new boundaries, just to prove that that really is the answer? What do? You take the inside, and you say, hey, inside, you got to be between negative pi over 2 and positive pi over 2, because that's where the boundaries originally are for tangent. Solve that for x to find out where the new boundary lines, the asymptote lines, end up being. So what am I going to do to solve for x there? X said, I want to be alone. So what am I going to do? Subtract pi over 2 from all 3 parts. Puts x alone. I can do the right side, 0. Pi over 2 minus pi over 2. The other side's easier too, because they already have a common denominator, huh? Minus 1 pi over 2 minus 1 more pi over 2 is minus 2 pi's over 2. We good? 2's cancel. See how x is between minus pi and 0? Am I going too quick? Is that good? So then when you go to do the graph, you'd have one asymptote here at minus pi, the other at 0. He does the snake going up. He doesn't have a negative. He has a positive in the front of him, nothing positive. So snake going up. But then remember, he's going to repeat that forever. That's just one of infinite snakes. So the next one, whoops, wasn't a very good asymptote line there. The next one is going to go from 0 to pi, and et cetera, et cetera. Is that good? See how that is discoverable? So then we can go back and say, okay, so he's the one that does that. They're probably going to show me mainly that piece, huh? Because that's the tricky, they're only going to show you one part or the other. 0 to pi part, let's see. So, yeah, see, there it is. There's the 0 to pi part. So, sure enough, that's number 2. Now, what about the other 2 graphs? We got 2 more to match up now. What do you think? Let's take this one. How about this one? Where do you think he goes? Is he 3 or 4? Yeah, which one is he? Yeah, how do you know he's 4?
Because it's just like normal y equals tangent x, but this time it's negative, so it's flipped.
Yeah, so notice they didn't move the asymptotes, did they? See how that's got to go with number 4? Because see how the asymptotes are in the normal place? I don't know if you can see that. Negative pi over 2 to pi over 2. It's just turned upside down. There's nothing plugged in but just normal x, so there's going to be no moving of the asymptote dotted lines. Whereas this one is number 3, because see how the asymptote lines have moved, right? The normal tangent asymptote lines are negative pi over 2 to pi over 2. See how this one is moved. This one has an asymptote here at 0 and another one at pi. It has moved its asymptote lines, hasn't it? So that's got to be number 4 because he's got something in there that's causing his asymptote lines to move. And we got him. We good with that? Feel like you could do that on a test, that kind of thing? That good? With a little more practice, of course. All right, so number 2. Why don't I let you try that? So remember what you're going to do. You're going to take the inside. That's the inside, huh? And you're going to say inside, you got to be between negative pi over 2 and positive pi over 2. And then solve for x. And that'll tell you where the 2 new dotted lines go to, which is almost the whole battle, isn't it? So solve for x there. How do you get x alone there? Divide by 2. It's a little awkward to divide by 2. Like in other words, I don't know what you're thinking, but you may be thinking this. You may be thinking, I mean, that's what I would be thinking. It'd be totally natural. Divide by 2, that's right and true and okay, but that's like weird looking, isn't it? I mean, like, what do you do with that? Doesn't that look weird? So I'm going to suggest a different way. That's okay. If you know what to do with that, great. That is right and true. There's nothing wrong with it. It just might be kind of weird looking to you and hard to deal with. What might be easier, instead of putting a big 2 underneath like that, what's another way to divide by 2? How can you multiply? What can you multiply that's going to be the same as dividing by 2? Yeah, if you multiply by half, I think it'll be easier. So multiply by half, that didn't look so good. Let me try that again. So multiply by half. Multiply. See, that's easier to look at. Multiply by half. It's the same thing. I mean, either way, if you're fine with the divide, if you know that dividing by 2 is the same thing as flipping up a half, great. You're right. That's true. It's all good. But if you want, just multiply through by a half. So whenever you have a fraction, it's easier to multiply by a fraction instead of divide. But either way. So that'd just be x. This would be pi over 4. This would be minus pi over 4. Are we okay there? So I just multiplied through a half, a half, a half. And that got rid of half of 2 is just 1. That got rid of the 2. So which of these graphs has asymptote lines at negative pi over 4 and positive pi over 4? Well, this one does. See him here? I don't know, can you see him? It's kind of small up there. Minus pi over 4 and pi over 4. But so does this one. That one also has, forget it, B's out, right? B does not have the, well, actually he does. They're being kind of tricky, aren't they? But he's just a dumb graph. No, he doesn't. No, my mistake. Do you all see that the asymptote lines are not? Yeah, B is out. See, the asymptote line is just to the right of pi over 4. That's not correct. It's supposed to be right on pi over 4, right on minus pi over 4. So we know no way for B. Right there, the asymptote is supposed to be right there, huh? So B's out. We're down to A and C. What do you think? What's the difference between A and C? They both have the right asymptote lines.
It's C because A's going down.
Yeah, A's upside down. See how A goes down to the right? What would make that happen? If there was a negative 1/3 in the front instead of a regular positive 1/3. It's a positive number in the front, which means it's going to go up to the right. The answer is C. Or if it was cotangent, If it was cotangent, that also makes you go down to the right. But then that has different asymptote lines. So there we go. Good, easy enough? On that. We'll keep going. Okay, so here's the cotangent graph. And remember, we already know the cotan, what he basically does. The cotan has his asymptotes, the normal cotan, between 0 and pi, and he goes down to the right. He's an upside down snake, because cotangent, remember, is upside down of tangent. Getting more and more comfortable with these trig functions. Remember which one is upside downs of which ones. All right, so that's the normal cotan. That's just normal cotan. But these are all moved around and stuff. So yeah, how about this one? Which one of them is a normal cotan with a negative in the front? What's that negative in the front going to do? Yeah, that's going to make it go upside down, so it'll actually go up to the right. Which of these go up to the right? Wait, a couple of them do. Oh, that one has a negative also. Okay. Yeah, I didn't see it there. So which one goes, though, but which one goes from 0 to pi?
Number 13.
13, so that's 13 for sure, huh? See how his asymptote lines are going right here? Here's an asymptote. Right on 0. This is pi over 2 in the middle, so this must be pi over there. So that's the negative cotan. Normal, non-shifted, normal asymptotes between 0 and pi, and the cotangent's been flipped up, so it's going up, actually. So there's 13. So then 14 is also going up to the right, so it's got to be the other one with the negative in the front, doesn't it? We good there? So now we're down to 2. I always liked match-up questions on exams, you know? You only had to know about half the information. You could match the rest up. So, okay. So now we got 2 more to go. Wait a minute. Do they look the same? No, they don't. My mistake. Oh, never mind. I'm off. Yeah, so one of them is going through the origin. The asymptotes are negative pi over 2 and pi over 2. The other one is not going through the origin. The asymptotes look like they're at 0 and pi, I guess, because that's, I don't know if you can see it, that's pi over 2 in the middle there. So this one's at 0 and pi. This one's at negative pi over 2 and positive pi over 2. Okay, so we got to figure out which is which. Let's just grab the first one. We don't really have to do one of them, huh? Let's just grab that first one, find out where his 2 new boundaries go, and boom, we're in business. So I'll do it over here. So y cotan x plus pi over 2. Cotan x plus pi over 2. So we take the inside. Same old thing. That's what we're going to do all section today. Just take the inside and put it between the boundaries. Now, what boundaries? Well, you put it between the original boundaries, and then you find out where they move to. What are the original normal boundaries for cotan? 0 and pi, right? Both the co-functions today, cotan, and when we get to cosecant in a few minutes, 0 to pi. For both the co-functions, 0 to pi. Yeah, so there we go. Can you solve that for x? X is saying what he's always saying. I want to be alone. It's a big loner. So, subtract pi over 2, right? And so what do we get? Well, this This is just negative pi over 2. These cancel. X is alone. What happens on the other side? It's a whole pi minus a half a pi. It's a half a pi. Or I'll do it more formally also, if you want. Right, this is pi over 1. So multiply top and bottom by 2. So then it becomes 2 pi over 2 minus, and then this guy, pi over 2, which is 1 pi, right? 2 pi's over 2 minus 1 pi over 2 is 1 pi over 2. Good? So the new boundaries are shifted. The boundary lines are shifted to negative pi over 2 and positive pi over 2 for this guy. So I'm going to go back. Basically we're looking for dotted line at negative pi over 2, dotted line at positive pi over 2, and cotangent is a snake going down. So which one does that? Well, that's 15, isn't it? There it is. So this guy here must be 16. We're done. Good.
How do you know if it's going to the origin?
Yeah, well, that just all has to do with the shifting. Yeah. So, like you can look at the normal graph. Yeah, it's all about the shifting. So, like this last one, where he did end up going through the origin, and that's just because the asymptotes centered him. The asymptotes had a middle of the origin. So it's basically, they're always going to go through the middle. Yeah, maybe I should say that more clearly. That's a good question. It's always going to go through the middle of their two asymptote lines. So if the middle of the asymptote lines happens to be the origin, it'll go through the origin. And it does. In this case, his two asymptote lines were negative pi over 2 and positive pi over 2. The middle of them is the origin. Yeah, so notice all the graphs. So if we go back to where I set them all up, see how they all go through the middle of their two dotted lines, don't they? All of them are in the middle, very middle of their $2. So if that very middle happens to be the origin, it'll go through the origin. Whereas in cotan, normally it's not the origin for the normal cotan. Good. Other questions on that one? All right. So number 6. So try that one. Multiple choice. This is exactly the way the real exam will be. So 5 cotan x plus pi over 6.
Is there going to be another part on the real test where there's no calculators?
I can't remember. Take a look at that practice exam. It's all on there. I forget. Because some of them we do and some of them we don't. I don't exactly remember.
And are you saying no graphing calculator?
Yeah, there's no graphing calculator. That part, yeah, I did mention that. Let me say that again. Yeah, no graphing calculator on this exam. Because there's a lot of graphs. It is valuable to know these by hand. It is helpful in calc. So do the same thing. Put that inside between the two boundaries and get x alone. Bring it over here. And so we take that inside. And we put it between 0 and pi, right? Because that's the normal boundary lines, asymptote lines. For cotan, all the cofunctions, cotan, cosecant, 0 and pi, huh? So I put it between 0 and pi, and then we solve for x. And so that would be subtract pi over 6. From all three, these cancel. X is alone. Minus pi over 6 there. Now the other side, we got to get a common denominator, right? You guys are already there? So this is pi over 1 multiplied not by 2. Just kidding. Multiply top and bottom by 6. So we get 6 pi over 6 minus pi over 6, which is, that's minus 1 pi over 6, right? So that's 5 pi over 6. 6 pi's over 6 minus 1 pi over 6 is 5 pi's over 6. So there's the two new boundary lines, minus pi over 6 and 5 pi over 6. So we're saying, okay, so this is a cotan graph. that's just got one boundary that's just a little bit left, just minus 1 pi over 6. And the other boundary that's pretty far right, 5 pi's over 6. So the middle of those two is not going to be the origin, is it? See how we know? So getting back to Vu, right? Vu's good question. How do you know when they're going through the origin? So this one won't, because the asymptote lines, the middle of the asymptote lines, I don't know exactly where it is, but it's not the origin, huh? It's going to be somewhere to the right of the origin. And so that's right, because the asymptote lines have been moved to minus pi over 6 and positive 5 pi over 6. It always goes through the very middle of the asymptote lines. Now, is this a snake going up or down? Yeah, because cotan, unless you put a negative in front of him, positive in front of him, goes down to the right, because he's upside down of tangent by nature, isn't he? So we're looking for that kind of graph. Let's go back and find it. That's what it should look at. Yeah?
What exactly does the amplitude?
Oh, yeah, good question. Guillermo, right? Guillermo. Yeah, that 5 in the front, good question. Yeah, 5 in the front, just like for, it might seem different. Remember what would a 5 in the front do last week in front of a sine or a cosine? It was the amplitude. It would go up to 5 and down to negative 5 instead of just up to 1 and down to negative 1, right? Make the sign go higher and lower like that. Well, it's what it does to any graph, it turns out. When you have a number in the very front, it just amps it up, literally. It just pulls it up, pulls it down, stretches it vertically. Now, the trick is on a tangent, it already goes up forever, So you're not going to see it a lot. It'll go up a little faster is what it is. It takes this arm and pulls it up quicker, and this arm and pulls it down quicker. It stretches it 5 times vertically. So it will end up looking almost straight up and down. You'll see that in the pictures. It'll go I'm probably not a very good drawer of it, but it ends up being almost straight up and down because it goes up and down faster. But it's not a big visual difference because tangent already goes up and down forever. Whereas like on sine and cosine, it really shows up because they have a ceiling and a floor, don't they? They have a top and a bottom. So yeah, good question. Let's go back and see. So what was it again? It was between negative pi over 6 and positive 5 pi over 6. So can you see those four? Wait a minute, I need some help here. It's going down to the right. I always say down to the right and not centered at the origin. Now, A and C look similar to me and almost both right at first glance. It's not B. Why is it not B for sure? B's going up to the right. That's not what cotan does unless you put a negative in front of him. And so is D. D's going up to the right. That's not right. So it's A or C. They both appear to have the right boundaries. Negative pi over 6 and 5 pi. Negative pi over 6 and 5 pi. Well then, what's the difference? They're both going down to the right. Down to the right. So what's the only difference between A and C? The stretch. See how C is more vertical and A is more snaky. It has more flat zone. See how there's more flattening in here? Right there, it's flat. So it's C. That is the 5 in the front. So I'm glad Guillermo asked about that because that turns out to be a game changer, doesn't it? The fact that it's more straight up and down makes it answer C, not A. You guys see what I'm saying? A is more flat in the middle like the normal tan or cotan. C's been stretched. It's almost straight lines. Good? It's making sense?
Why would it be, how would the 5 affect that so that it would make it more straight?
Oh, it's just because it's multiplying all the numbers. Yeah, whenever you have 5 in the front, imagine if you have y equals 5 times blah, 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 whatever. If you were to make a table and plug in a number, imagine any function you want. Sine, let's just do sine of x. If you plug in 30 degrees or whatever, if you just had sine, it would be the sine of 30 degrees. What's the sine of 30 degrees? Can you all do that off the top of your head now? What is it? That's the angle. 30 degrees is pi over 6. So what's the sine of pi over 6? Or what's the sine of 30 degrees? What's the answer? That's the angle.
1/2.
It's a half. It's a half. So the sine of 30 degrees is a half. But if you put a 5 in the front, it's going to be 5 times a half, isn't it? See how it's just going to multiply all the y values, all the heights, by 5. That's why it stretches it. It's just going to multiply all the y values by 5, isn't it?
So if there was no number in front of there, it would just be, it would be A.
It would be A. Yeah, if there was no number in front, it would be A. Exactly right. Good point. It would be, if there was no 5 there, then our answer would have been A, huh? Because that's the normal cotangent. Exactly. All right, so we have 1/3 cosecant x over 3. Look at that. U-shapes everywhere. What is up with that? All right. Well, let's talk about it. So, what have we learned about cosecant? In fact, let me just rewrite it on a fresh screen here. Number 8, 1/3 cosecant x over 3. All right. So, what have we learned? Cosecant, remember, both the cofunctions have their asymptotes between 0 and pi until they're shifted, right? Both the cofunctions, cosecant, cotangent. So, and cosecant, instead of doing snake, the snake is for tangent and cotangent, right? Cosecant does a U shape at 1 going up, and then a U shape at -1 going down. U up, U down, U up, U down forever. But the first boundaries are 0 to pi. So what am I going to do? Same thing I did in all the rest. I'm going to grab the inside and say, hey, inside, your normal boundaries are 0 to pi. And then solve for x to find out where the 2 first normal boundaries move to. That's good so far? So that's just like the other ones. This is what you always do for all 4 of these. You just grab the inside, you say between the 2 normal boundaries. So how do you solve? Now, MathXL will give a different game plan here. For secant and cosecant, they have you do period and some other stuff, which I don't think is nearly as easy as just doing the same thing we've been doing for tan and cotan. But just heads up, you click the help button, they'll talk about the period and other stuff, kind of like we did for sine and cosine. But I think this is easier to stick with the same game plan. So we want to get x alone. Multiply by 3, huh? Because if you go times 3, it'll cancel that out, won't it? So times 3 all the way across. Good there. What's 3 times 0? 0. And 3 times pi is just 3 pi. So the boundaries move, don't they? They move to go from 0, I'm just going to draw it in the same place and call it 3 pi now. 0 to 3 pi. They move from 0 to pi to 0 to 3 pi. Now, everybody good to there so far? What do you think is the effect of that 1/3 in the front now? What have we said numbers in the front always do? Heights, huh? Yeah, they affect the heights. They affect the y values. So it's just going to make him 1/3 as high. Now, where does cosecant normally hit height-wise? 1 and -1. So just times both those by 1/3. So now it'll be down here at 1/3 and a U shape going up. And here at -1/3. Whoop, not there. Over here, U shape going down. Rid of that. Etc. Is that making sense? So for cosecant normally hits at 1 on up as a U shape and -1 on down as a U shape going down. But now he'll hit at 1/3 and -1/3, meaning really close to the axis, just barely above, barely below. U shape up, U shape down between 0 and 3 pi. It's the new boundary lines. Let's go back and find it. Can you tell which one it is? Yeah, you see how A and C are doing weird things? We'll talk about what they're doing. They're not even centered on the x-axis. Do You see that? See how the x-axis is the middle of my graph? The x-axis is not the middle of their graphs? That's wrong. That's a vertical movement. We'll get to that. That's not what we have here. A and C are crazy. B is our answer. See how it's a U shape? Just barely above? That looks like 1/3, huh? It's just barely, I mean, I can't exactly see it's 1/3, but it's barely above. And the lines are between 0 and 3 pi. And the next one's barely below. And it goes out 3 pi more, so 6 pi. That makes sense. So it's good. U up, U down, U up, U down, etc. We all good on that? So the real exam, number 2, will be just like this. I mean, you'll have a D option. But on the graphing ones, I will not put an E option. And none of the above. I know you're going to miss those. You really enjoyed those on the first exam, huh? No, and they'll be back. Don't worry. They'll be back. But for graph ones, I'm really not trying. I don't want to fool you, but I just have to discern what you know. So I don't want to fool you graph. Like, I don't want you to be confused because graphs can be a little tricky to read. You know, I don't want you to look here and go, hey, that looks right, but how do I really know that's 1/3? Maybe that looks like 1/4. And Mr. Heron's trying to trick me, and I should do the E, none of the above option. I'm really not trying to be that tricky. But just to make sure it's clear, there will be no E, none of the above option on the graphs. Therefore, you know it's one of those 4. So with that in mind, oh, well then this one's better than any of the others. I can't exactly tell that's 1/3, but certainly not the other ones. So you'll know. It'll be just like this. You'll know. You won't have to be, really weird about finding 1/3 or something. Okay, in fact, let me just put it on first screen. Number 9. Y equals secant x over 4, is that what it is? Yeah. All right, so let's try that one. Okay, so I take this inside here and I go inside. You're between, now what, if it was cosecant or cotangent, I would write 0 and pi. But it's not co. So then I'm going to write negative pi over 2 and positive pi over 2. Right? We good? That's what you always do for non-cos. For the secant and the tangent, it's between negative pi over 2 and positive pi over 2. Now we got to solve for x. X wants to be alone. What do I do to solve for x? Multiply through by 4, right? We all good with that? Because that's the... notice we always do the opposite of whatever's going on with x. If x is being divided by 4, the opposite of that is multiplying by 4. If x has a number added, we subtract. If x has a number subtracted, we add. X has a number multiplied, we divide, right? We always... Do you know that from your algebra days? You always do the opposite to get x alone. So I'm going to multiply through by 4. Okay, so then I get minus pi over 2 times 4. In the middle it cancels. That gets x alone. And positive pi over 2 times 4. Now, how do you multiply like a fraction like minus pi over 2 times 4? What do you do when you have a whole number and a fraction interacting? Put it over 1. Right? Now, do I need to get common denominator there? Not for multiplying, right? Only for adding, subtracting. For multiplying, no common denominator is needed, and what are you allowed to do? Cross cancel, right? 2 goes into 4 2 times, minus 2 pi. Everybody clear on the difference in the rules between multiplying fractions versus adding, subtracting? Adding, subtracting requires common denominators. Multiplying, not needed. And you can cross cancel, which is nice. Over 1, 2 goes into 4 2 times, positive 2 pi. So there's the new boundaries. So that means between negative 2 pi and positive 2 pi, we got secant doing his thing. Now what does secant do? What is his thing? Yeah, not a snake. That's tan and cotan. Secant and cosecant do the U-shapes. U up, U down, U up, U down. So right in the middle of those asymptote lines, which is going to be on the y-axis, isn't it? Straight up, U-shape, that's going to be at a height of 1. Because that's where secant and cosecant are, unless there's a number in the front to shift it. And then a U-shape down at negative 1, etc. Let's go see which one has that between negative pi over 2 and positive pi over 2. They've all got that. It's miserable. No, actually, no, look, he's right on the axis, right? He hits in the middle of the y-axis. See that? So, no way for A. He doesn't hit, right? The center of his U right here. See this right here, this point? That's not on the y-axis like it's supposed to be, right? See, ours is on the y-axis. See that? So it's not A. B's looking good. Let's keep looking. C. See that? No. D. It's there, but it's going down. It's on the y-axis, but it's a U down. B, I mean, B's got what we want. There's the center of the U shape going up on the y-axis. B it is. Everybody see that? See how we grab that? Questions? Now, what's that red thing they're putting in there? Can you see that? Oh, that didn't do anything. The reason this is right, the red is a cosine graph. Let's just say cosine of x. Well, it's whatever. Cosine, it's basically a cosine graph. So what does that mean? If this, what is this height? If this is cosine, what is that height? 1. And this is 0 on the cosine graph, right? 0. This is -1 height. Okay, so if I take the, remember, secant is 1 over cosine, right? That's what secant is. He's the flip of cosine. Okay, so what? Well, imagine if you take the cosine numbers and flip them. What if you take 1? So I'm going to take the red numbers and flip them. So here I get a 1 for cosine, then a 0. And in fact, let's go halfway through there. This is 1. What's this value? Let's just say half. Somewhere there's a height of a half, right? And this is 0 height. And then this is -1/2. And this is -1. Hold on, is what I'm doing making any sense at all? These are the cosine values, and I'm going to put next to them the secant values. Let me hold on. I'm just tracking through that, like I'm riding on the roller coaster of the cosine, the red cosine. I'm saying I'm at the top of the roller coaster right here. I'm at a height of 1 right here. And then I start coming down the roller coaster. I'm at a height of a half at some point. I don't know exactly where, but a height of a half. And then I'm at a height of 0, -1/2, -1. I'm just taking one section of the cosine graph and say, what's going to happen to those heights as you flip them into secant? Because that's what secant is. It's just the flip of cosine. You take 1 and you flip it. It's 1 over 1, which is still just 1. That's why the blue dot and the red dot are right on each other there. You flip 1, you're still at 1. But what if you flip a half? 2 over 1. 2. That's why this half is up here at, see it up there? It's up there at 2. It's above. It actually goes up. The flip of a half is 2. See why the secant graph starts going up? What happens if you flip 0? What's 1 over 0? What's 1 over 0? It's undefined. You can't divide by 0. 0 goes into 1 infinite times. 0 goes into 1 forever and ever and ever. That's why you get this vertical line. You can't flip 0. Do you see that? When the cosine is 0 and you try to flip it, that's where you get the vertical asymptote lines. Let's flip -1/2, -2 over 1, -2. That's why at -1/2 it's down here at -2. See it down there? And at -1, you flip that, still just got -1. So right here, they're on top of each other, aren't they? Etc. Do you see how you're going to get those U-shapes going up and down? And the vertical asymptote lines? That's where that stuff comes from. That's why secant does that. He's just the flip of cosine. So if you just take those cosine values, because if you flip fractions, they become bigger than 1, don't they? You flip a half, it's 2. You flip -1/2, it's -2. So in other words, the lowest value is going to be 1. You flip 1, it's just 1. That's why they touch at 1 and -1, don't they? Because the flip of 1 and -1 is still just 1. But at all the places where cosine is smaller, like a fraction, secant becomes bigger because you're flipping a fraction. And where cosine is 0, see everywhere where cosine is 0, we have a vertical asymptote line for secant because you can't divide by 0. That's infinite times. That's why that happens. Okay, so try that one. Forget about that -1 for now. That is the part that's new, and I want to show you about that. You might already know. But just do the regular first off. Let's just do the regular. And what do I mean by the regular? You grab the inside, and you say, hey, inside, right? Always the inside the parentheses. Inside, you got to be between what two boundaries?
Pi over 2 and negative pi over 2.
Yeah, because it's a non-co. It's like tangent. Negative pi over 2. And positive pi over 2. All right, solve it from there. Those will be your two new boundaries. All right, how are we doing? So this is a little harder. What do we got to do to get x alone here? What's my first step? Subtract the pi over 2. Good with that? So subtract pi over 2 from all three. So these are gone. And so then I get 2x in the middle. Okay, over here, minus pi over 2 minus pi over 2, that's just 0. That's easy. Now what happens on the... Oh, wait, no, I'm confused. This one's 0. And the other one's minus 1 pi over 2 minus 1 more pi over 2 is minus 2 pi over 2, which is minus pi, huh? We're good so far? Everybody see what happened over there? Right? That was minus pi over 2 minus 1 more pi over 2 is minus 2 pi's over 2. Those cancel. It's just minus pi.
That wouldn't be pi over 4.
I'm not, x is not alone yet, notice. Are you meaning like already?
Yes, already.
So I'm just saying, so what is minus 1 pi over 2 minus 1 more pi over 2? So when we add, subtract, we don't mess with the denominator. Right? It's minus 2 pi over 2. Does that make sense on that? Yeah, we don't mess with the denominator when we're adding, subtracting. Right? Like 1/3 and 1/3 is 2/3, huh? It's not 2/6, because that'd be back to 1/3 again. You with me? Making sense? So you just do the numerator. You keep the common denominator because that's what's true. That's what's real. Like you have a real pi, and you have 1/3 of a pi, 1/3 of a pi. That makes 2/3 of a pi, not 2/6, huh? That's what's true. Good? Good question. Everybody good with that? So then now, how do we finish getting x alone? Now we divide through by the 2, and 0 over anything is just 0, and now this is minus pi over 2. So there's the new boundaries. It's going to be between minus pi over 2 and 0. Everybody good there? So far, so good. So we're going to draw a graph that basically has one boundary at minus pi over 2. Wait, I'm not doing a very good job on this graph. Let me do a better job, because we do need to think about this one kind of carefully. So we're going to have one boundary over here at minus pi over 2, and the other one at 0. So minus pi over 2 and at 0. And let's forget about the minus 1. I'm going to pretend it's not in there for now. What will the graph do? It's secant. So what will it do between those two boundaries? U-shape right in the middle, huh? Right here. U-shape going up, and then over here, U-shape going down. And this will hit up at 1. This one will hit down at -1. Right, because there's no number in the front. There's really just an invisible understood 1 in the front. So nothing's going to change so far about where it hits. We good so far? In other words, if this was something like a 3 in the front, then this would be at 3, wouldn't it? And this would be at -3, huh? Right? Because that multiplies the y values, whatever number's in the front. So we just have a visible, understood 1 in the front. So it's going to hit a 1 and -1. so far. But now's the new part I wanted to show you about. But that part was tricky too. Questions? Anything else I can answer so far? Now, what about the fact that we have a negative 1 out there? Do you remember what that did for sines and cosines? That was like the D. Remember, this was A, B, C, and I called it D. It was like the last thing we looked at. Numbers added and subtracted outside of the parentheses after the trig function, you know. What does that do to the picture, the graph? Does what? Moves it up and down, huh? It actually slides it instead of stretches it. Are you seeing that difference? The number that's in the front here, that leaves it centered where it was centered and stretches, but the number out here actually moves the whole thing. Did you get the difference? I mean, what I'm saying, it'd be like if I had a little piece of plastic, right? And I could leave it anchored to the table and stretch it, or I could just move the whole thing up into the air. Those are two different kinds of changes, right? Numbers in the front here stretch things, but they leave it anchored where it was anchored. They don't move its center. But numbers out here move the entire graph up or down. So this will move down 1. The whole graph will move down 1, the entire thing. Let's grab the whole thing and go down 1. So this 1 is going down to 0, huh? Going down to 0. And this negative 1's going down to negative 2. And of course they go down forever and up forever. And there it is. The black one's the real one. You see what happens? See how we move the whole thing down 1? Another way you could think of it is the new center is at negative 1. It used to be the y-axis, the x-axis. The whole thing moved down 1. The new center is down 1, isn't it? So that's how we did the sines and cosines. We found the new center. That's right. I called it midline, didn't I? I said find the new midline. New midline's down 1. You can do the same thing here if you want. The new midline here is down 1. This is the new middle for this black graph and this black graph. Everybody see that? So let's go find the one that does that. The asymptotes are between negative pi over 2 and 0. And it hits on the axis and then at negative 2. It's just hard looking at them all at once. Let's just do it. So let's just look at A first off. Is A right? Where were the asymptotes again? Negative pi over 2 and 0. So is A right? Oh, wait. The U-shapes aren't even the U-shapes are not right. Yeah, there's supposed to be one of them at 0 and one of them at negative 2, huh? So maybe that'll be the best thing to look for. 0 and negative 2. So these are both negative, aren't they? That's not right. You guys with me? This one is 0 and negative. Oh, that looks good. How about this one? 0 and negative. That looks good. These are both negative on D. See how D, both the values are below the axis? That's not right. So A and D are out. I kind of do elimination. A and D are out. Because you're supposed to have a dot at 0, like that one does, and a dot at negative 2. So these, both B and C, are looking good. They have dots at a height of 0 and a dot at a height of negative 2. The two center dots are at height of 0 and height of negative 2. Now, which one is the real deal? B or C? We're going to have to look at where exactly, like, let me go back here. This one hits, it's between negative, whoops, I'm erasing it. It's between negative pi over 2 and 0, asymptotes. Asymptote at 0. That looks good. The U up is left of 0. See how this U is to the left side of the middle? The up is to the left. See how the up is to the right there? C's out. See, B is showing his up right there to the left. It's B. That was a little tricky. Does everybody see that last little distinction I made? Right? See how B has his U-shape to the right, C does, has his U-shape to the right of the middle. Right? That U-shape is to the right of the middle. No. The U-shape is supposed to be left of the middle, isn't it? Because that's where the main asymptote lines were. Negative pi over 2 up to 0, left of the middle. So the answer is not C, it's B. Even though they're not really showing the one to the left, you can tell it's starting to be there. And this one's to the right, which is correct. This one's to the right. B it is. Is that good? That's probably like the hardest graphing one right there. Good on that? You feel like you could do that on a test? Recognizing these things? A little practice? You practice. You can ask for more of these on the homework. You can ask for more. And then the practice exam, you can practice those. Yeah?
So it seems that both cosecant and secant, the first u that you place is always going to be upwards.
Yes, absolutely. John's point is a very good one. For both secant and cosecant, when you do the u thing, the first main asymptote line, the first u's up. And that's really good observation. That's why we take all that effort, like right here when I said, take the inside and put it between, I did all this work. That's because those boundaries you end up solving for are where the first u up, not down but up, right on, John, always go. So when I found these boundaries, I put the u up. And that's what made the difference between B and C, huh? Exactly right. The first u is always up in the main new boundaries you find when you do secant and cosecant, right?
If it was negative in the front, would it be...
And if it was negative, that would make it down instead, like always for all the graphs. That's right. Absolute value in there. What is absolute value? So if you have a number like -3 and you put absolute values around it, what does it become? Positive. It just makes everything positive, huh? Y equals absolute value, which means y equals only positive, huh? No negative y values. Look at this. That's not going to happen. See how that's below the y-axis? I mean, that's negative y values. See this right here? Negative? No way. Right? No negative y values. So first off, they're out. A and D are out. Because absolute values mean only positive. Oh yeah, and B's out. They're all negative on B. I didn't see that until you pointed. Yes. Thank you. Jamie, right? Yes, B's out. So there it is. C. Done. Next problem. It's the only one where they're all positive. Right? C is the answer. It's the only one, only positive. Good. That was easy. Could have been absolute value of anything. We would have known the answer had to be C there. All right. Are we good? All right. An ambulance with a rotating beam of light is parked 10 feet from a building. The function d equals 10 tangent pi t. Let me write that here. D equals 10 tangent pi t describes the distance d in feet of the rotating beam of light from point C after t seconds. Graph the function on the interval 0 to 4. Graph the function on the interval 0 to 4. Okay. All right, so they're giving me a function. D equals 10. That's a funny looking 10 now. 10 tan pi t. Now, I hope that's not confusing. Normally, we would see y equals 10 tangent pi x. It's the same thing, right? The t is just playing the role of x. It's time. So this would be like a physics. This is very much a physics problem is what it is. And the d is like the y. He's representing the distance. Same thing, whatever. All right, so how do we, and they're saying which one, A, B, or C, which one's the right graph? Well, how do we graph a tangent function? What do we do? Grab the inside and say, hey, inside, pi t, pi x, same thing. You got to be between. He's a non-co. Negative pi over 2 and positive pi over 2. Good so far? And then, can you solve for t there? T is like our x, right? We always want to get x alone. This time it's t. T's saying, I want to be alone. So let me let you do that. What do we do to get t alone?
Divide by pi.
Yeah, divide by pi. That can be a little awkward looking. I mean, it's fine if you're good with that. Just divide by pi, divide by pi, divide by pi. But that might be, I don't know if that looks weird to you. It's right, it's true. If it bugs you, instead of dividing by pi, if it's easier for you, what else could you do? Excuse me. Excuse me again. Exactly. You could say, let's just divide by pi. That's the same thing as multiplying by 1 over pi, huh? That's totally right, right? Dividing by pi is the same thing as multiplying by 1 over pi. Dividing is just upside down multiplying, isn't it? So that might be easier for you. So then t's alone. And over here, what happens? The pi's cross cancel and you get a half. The pi's cross cancel and you get minus a half. Is that good? So the time, the t, is between minus a half and positive a half. No more pi's. Those are actually in seconds. See up here it says time is in seconds? So between minus a half a second and positive half a second. So we got a tangent graph. So that means when you draw the graph, you'd have one asymptote line at minus a half a second. Another at positive half a second. Tangent, what does tangent do in the middle of his asymptote lines? He's a snake. He goes up to the right because this is a positive 10 in the front. It's going up to the right. Very fast, though, huh? That 10 is going to make it go almost like a straight line. You can see how these graphs are that way. So which one is going up to the right between minus a half and positive a half? It's not B, is it? B's going, notice B's going down to the right. I like to just eliminate things right off the bat. So forget about B. B is going down to the right. See how these are going down to the right? That's like, it's not right. We're supposed to go up to the right. So it's not that.
C starts at above 0.
Oh, yeah, good eye. Yeah, it looks like, see how C right here? He's hitting above the origin, whereas we know ours has to hit right on the origin. Why? Because it always goes right in the middle of its two asymptote lines. So, yeah, so it does have to be A. Good observation. Everybody see that? We good to there? Tangent, okay. Let's keep moving. We have more parts to this one, if you're good with that. So for what values in 0, 4 is the function undefined? When is the function going to be undefined? Look at the graph. Undefined means the vertical dotted line, right? That's where it's, so this, right here, it's undefined at a half. Okay, so we got to think about, in fact, maybe I should, where will the next, okay, it's getting off the screen, huh? Let me draw that again with a little more room to the right so we can think about it. So minus a half and a half. It's going to do its snake thing. Now, where's going to be the next dotted line, knowing that it goes forever? Another snake here. Where's the next? If this one's at a half, how do you know where the next one's going to be? This width has got to match that width, right? It's not going to get wider or narrower. Wider or more narrow. It's going to be the same width. So what's the width here? How far from negative a half to positive a half? 1, right? Back a half, forward a half. That's a half and a half's a whole, right? So if this width is also 1, then the width is always 1 between the two dotted lines. We good so far? Then if this is a half and you jump forward 1, where are you at? 1.5, huh? Or 1.5, if you want a decimal. Make sense? That good? Everybody see that? Right? The gap between, the width between the two dotted lines, if it's back a half and forward a half, has got to be 1. So therefore, they're always 1, 1, 1, 1 to the next dotted line, aren't they? So if you're at a half, the right edge, and you go forward 1, you're at 1.5. And if you go forward 1 again, you're at 2.5. And you go forward 1 again, you're at 3.5. Aren't you? And those are all the places where you're going to have a dotted line. And so those are the undefined places. They're asking me to give the values between 0 and 4. Notice I didn't even talk about this negative half. Why? Because it's not between 0 and 4. They're saying, just tell me the places between 0 and 4. So if they just want the answers, the t values between 0 and 4, where it's going to be undefined, that's what they're saying, then it's going to be at 1/2, 1.5, 2.5, and 3.5. That good? So, oh, and you can just make that a decimal. We want to make them all decimals, whatever. Yeah, oh, they say decimals, yeah. Type integers or decimals. See how they want decimals? So I'll give them these decimals at 0.5, 1.5, 2.5, and 3.5. We good? Is that making sense on that? Questions on that one? Was there a part C? Let's see if we can kind of lose track of reality. What does this mean about the rotating beam of light in the figure shown, this picture? So we just gave the answer to part B, that at 0.5, at 1.5, at 2.5, and at 3.5, etc., the function is undefined. So what does that mean about that light, that ambulance siren light?
It's not touching the line, but it's really...
Do you ever driving down the road in your car and you look up and you see the flashing lights? I have. It's always an unnerving feeling, the flashing lights, right? And then then do you ever think maybe it's undefined? Like, what does that mean for a siren light to be undefined? I mean, what are we doing this weird old math thing? This undefined. How is that reality? So what do you think? Kevin, do you have a...
that it's not like touching the line or the wall in this case, but it's like really close to it.
It's not touching, but it's really close to it? Yeah, I think you're on the right track. Yeah. How about we, since we have a minute, why don't we look at that picture and think about where they come up with this formula and try to be real. I don't know if any of you are going towards engineering or science or something like that. You're going to take physics. This is basically a physics question. In fact, I'm doing some physics with my daughter right now. She's taking physics, so I'm kind of like taking physics with her. So if you're going that way eventually, let me do a little. Where'd they come up with that? It's not going to be that hard. It's not anything outside of what you already know. We'll just use what we learned in the first part of the course. All right. So this little siren's going around. This ambulance light is going around, and as it goes around, the light moves along the wall. Right? That's what's happening. That's what we're talking about, is how as you watch that siren light move along the wall as it turns. Right? Okay. The D is the distance where the light is currently along the wall from C, the closest point. You tracking with me? So it'd be like if I took a flashlight and I shined it on that door. That's probably the closest point to me on the wall. And then I started moving it to the right. And I said, I want you to tell me how far is it from the door. You know, it's 1 foot, 2 foot, 3 feet, 4 foot, 5 foot. You know, as I'm rotating, how far is the light from the door? So as this siren rotates and the dot moves, how far is it from C? That's what the D formula is. How far is it from C, the closest point on the wall? Well, how do you figure that out? They just set up a little right triangle. You guys are pros at right triangles. They just set up a right triangle. And they said, well, look, this is 10 feet. They just measured. Real life, you just measure. Like physics, you just measure 10 feet from the wall. The siren is 10 feet from the wall. The distance then, now this is pi t. How'd they come up with that? Well, basically, they said that thing rotates. Pi t, what does that mean? That means every 2 seconds it goes all the way around. Yeah, that just means every 2 seconds it goes all the way around. Right? If I told you pi t, what does that mean? When t is 2, the light will be at what angle? 2 pi all the way around. That means that light goes all the way around every 2 seconds. Am I making any sense? The angle here, see this angle, pi t? That's just, they're just watching, so you, in real life physics, you would just watch that light with a little stopwatch and say, hey, that siren light goes all the way around every 2 seconds. 1001, 1002. 1001, 1002. So that formula pi t represents that. Why? Why is it? Because when t is 2, if you plug in 2 here, you get 2 pi. The angle's gone all the way around, hasn't it? Every 2 seconds. So that's all that's representing, just telling you where they got that, real life. So there's the angle. At any point in time, like at 1 second or half a second, where is it? Okay, now. And then they just set up a little right triangle. Now, and they're trying to find D. So here's my angle, theta. This is D. This is the opposite. This is the adjacent. This is the hypotenuse. So what trig relationship could they set up to find D using the 10 and using the angle? Opposite and adjacent? Tangent. Remember SOHCAHTOA? SOHCAHTOA, tangent is opposite over adjacent, right? Tangent of the angle pi t is opposite D over adjacent 10. You see that? Tangent of that is opposite over adjacent, isn't it? Okay, now what do they want to solve for? They want D. They want you to solve for D. How do you solve that little formula for D? Put this over 1. Remember when you have a fraction and hold it, put over 1, cross multiply, remember that kind of thing? The 10, put the 10 in the front. You could put the 10 in the back, but it looks like it's in the tangent. So it's better form when you're dealing with the trig function to put the number in the front. 1 times D like that, which is D equals 10 tan pi over t. There's that formula that they gave me. But I want you to see where they came up with that. You see how they derived that? It's not amazingly deep math or anything. It's just trig, right triangles, do that thing. Okay, now that helps us to know what's going on in the real world with that angle. At half a second, when t is a half, we said it's undefined. Now, what does that mean, undefined? Well, look at that angle. When t is a half, when you take pi t and you plug in for t there, a half. What is half a pi? What angle is that? What's pi? What angle in degrees? Pi is 180, right? Remember pi radians is 180 degrees? So what's half a pi? How many degrees is that? 90. So you understand what I'm saying? At half a second, which we said is undefined, at half a second, half a pi, time is half a pi, half a 180, it's a 90-degree angle, isn't it? At half a second. So what? Yeah, the siren light won't touch the wall. You with me? If it's just 89 degrees, it'll touch way down there somewhere. But when it hits pure 90 at half a second, it won't touch the wall at all. What is the distance? Infinite. The distance along the wall? Infinite. That's what the undefined means. See how that happens in the real world with things that go around? That's why we made trig. Because things in real life, not just sirens, but all kinds of things in the real world, go round and round, up and down, back and forth, and we need something to represent them. But we also get that weird undefined state. Is that good? That makes sense? So what it means, let's go back and answer the question then. So, do we have it on the screen somewhere? There. So what does it mean? Let's go through it. The beam is shining parallel to the wall at these times. Is that true? Yeah, there it is right there. Yeah, the beam is parallel to the wall. At half a second, it's at half a pi, 90 degrees. Parallel to the wall. 2 minutes. Let me just help you set up. So giving you a picture. The figure shows blah, blah, blah. Oh, yeah, I should make that picture a little. Okay, so number 15. With our last minute and a half here, let's solve for D. D is this side of they're giving me the picture, that's nice. X is that little angle there, I don't know if you can see all that. So, wait, am I missing? Oh, and this is 6 over here. So what trigger, this is the adjacent side, this is the opposite, this is the hypotenuse. So I need a trig relationship that involves the D, the 6, and the X. That's hypotenuse and adjacent. What's that? Cosine, right? Yeah, good job. SOHCAHTOA, cosine is adjacent. So the cosine of the x angle is adjacent over hypotenuse, which is what? Adjacent 6 over hypotenuse D. Adjacent over hypotenuse. That good to there so far? And I need to solve for D, because they want d alone. Put this over 1, cross multiply like we just did for the ambulance one a minute ago. That'd be d cosine x is 1 times 6. Good so far? Just cross multiplied there. Last step, that d wants to be alone. What do you do to get d alone? Divide by the cosine of x. So d is 6 over cosine. Or the other way you could put that is 6 secant x, because 1 over cosine is secant, huh? Both those are right in my mind. I don't know if Math Excel will accept both. They probably want the secant. They're both right, though. Does that make sense, that little solving I did there? So the rest will be the same.